Hello, this is Dr. Flight, and this video will be an introduction to discriminant analysis. So let's go ahead and begin. We're talking about multiple discriminant analysis. We're talking about using non-metric dependent variables which have different levels available to them. So like a low, medium, or high, or maybe different group classifications, and then a series of metric independent variables. So we can have a lot of different applications of this, certainly in marketing. Ideally, what we want to be able to accomplish at the end of the day is to be able to assign objects or customers or whatever we're studying in terms of our unit of observation. We want to be able to group them or place them into appropriate groups without any prior information except for the independent variables. So discriminant analysis then is a set of linear equations. Now this is not multiple regression. This is a situation where we're grouping objects based on their similarities to some extent. So we're creating equations that have weights associated with them that are similar to the beta weights that you'd find in regression, but they're not exactly that. What we want to be able to do again is to be able to predict or place objects into classifications or groups. So we want to predict class membership for new observations based on some historical data that we have. Stated differently, discriminant analysis estimates the linear relationship between a single non-metric variable and a set of metric independent variables. So what will eventually happen when we run a discriminant analysis is we will create a series of functions. In this case, the function is noted by z sub j sub k. And then we have a as a constant in this function. And then we have different weights, w, and different independent variables, x's. So those w's are the weights. They, again, could be thought of as the beta coefficients, but they're not. They're slightly different. They are used to calculate a probability that an object would fall into a specific class. Okay, so this is so these z scores then are what are produced as the function, and so yeah, we'll get into these more later, but this is basically the setup of what will be defined as the model that we'll ultimately look at. So discriminant analysis is like but not linear regression. As I've already noted, the dependent variable is non-metric, so that would violate the regression rule of normality in terms of the distribution of both dependent and independent variables. So what will happen again is there'll be a function that's created for each level of dependent variable minus 1. So in other words, if we have 3 levels, we'll have 2 functions that are estimated. And then based on those 2 functions, our individual objects will be placed into the 3 different groups. If we had 4 levels, we would have 3 functions, and so on. Another alternative would be something called cluster analysis. And discriminant analysis is used to numerically predict membership into a specific group based on how close or how far apart the individual object is to what we call a centroid. So discriminant analysis then is a grouping mechanism or a classification mechanism, which is within sort of a category or group of cluster analysis tools that we could certainly be used. But what will be important in this is the function that is created, which then which is most efficiently created in order to classify objects around what we call a centroid. So that'll be a term that comes up from time to time. So there'll be some graphic representations that we can actually take a look at. So if we look to this graph on the left where we have x1 and x2, imagine that x1 and x2 are scores of some type, and then we have two different groups of objects, maybe consumers, people who maybe we have consumers who buy and consumers who don't buy, and they behave differently based upon the x1 and x2 scores that are created. And so what we end up with is sort of, if you look like towards the middle of x1 or A and the middle of B, we'd have some center point, a centroid, and then what we would have are objects that are closely associated with each of the different centroids that are there. Again, what we'll end up creating is some form of what we call a discriminant function, and actually in this case we have one discriminant function. We have two different groups, so we have two levels, an A and a B. 2 minus 1 is 1, so we have one z-score, which would be reported, and it's kind of indicated here. This is the the discriminant function and this would be the z-score. And what we can see is that we have the distribution here of A, and then we have the distribution of B kind of down below here, and you'll see how the centroid or the center point for A is different from the center point of B. So if we took this and we looked at it up above here to the right, we would see that the centroid distance is really what's being used to define these two groups. Now there is some overlap, right? There's some overlap there, just like there's overlap in the middle right there. But we are confident, based on the data that we've collected and the analysis that will be run, that these two groups distinguish themselves or discriminate from each other based on their relationship to A's centroid and B's centroid. So that is in essence what we're looking at when we think about discriminant analysis and the regrouping of objects based on this idea of a z-score. Here's a little bit of data which we'll see again, and this is data that was from a survey that consumers made on a 0 to 10 scale based on different product features that they feel are important to them: durability, performance, and style, X1, X2, and X3. We also have in this data an indicator suggesting whether the consumer would buy or would not buy this particular product. So in this particular data, this fictitious data here, 5 of the subjects indicated they would purchase and 5 said they would not. And we have 3 other variables. So the dependent variable would be, it would be like a dummy variable, like they either would be in group 1 or group 2. So this is like a grouping mechanism here. They're either in group 1 or group 2. And then there are 3 independent variables, durability, performance, and style, that combine to help predict whether the consumer would be in one group or the other. And you can tell, or you can look here at the different group means between group 1 and group 2 on each of the 3 independent variables. So group 1 and group 2 clearly differ by durability. So durability is very important to those who would purchase, or they perceive anyways the product as having more durability, and they're likely to purchase as a result. And very different for the group who are not willing to purchase. They perceive the average in durability to be much smaller, and we see this big distinction here when we look at the difference between group means. We see still a difference here in performance as well, but we don't see much of a difference here. So just as a preliminary type of a thing, we may think that these first two variables will be important in distinguishing group 1 from group 2, and we may find that this last one, style, may end up being non-significant and not really an important feature that would help us distinguish or differentiate one group from the other. But our job is to put the data into an analysis to determine that and come up with what would be the very best function or Z formula score that would help us determine who should be in which specific group. So that's the nature of this. We also will have features where we can draw these graphically, which we've already seen a little bit already in terms of graphical or spatial interpretations. So we will place these objects in a 2 or 3 space area and map them a lot of times. That's oftentimes a feature of discriminant analysis, a visual display, which helps us understand how the data forms a little bit better. So we create a 2 or 3 space dimensional map, if you will, and then we plot those pieces, those individual cases, based on their Z-scores for each function that's created. Again, there'll be, so if we have 3 levels, we'll have 2 functions. And so that would be the X and the Y axis on a determinant map, if you will. So that's how that we note that there will be some overlap between groups, like we saw in that last example. However, one of the features that we'll see, or one of the requirements, is that individual groups have to be mutually exclusive. So in other words, an individual cannot be in 2 groups at the same time. Even though there's some overlap, it only means that there's some shared probability that they may be in group A or they may be in group B, but at the end of the day, in reality, they can only be in one or the other. That's kind of the interpretation that'll follow. So again, looking at our map here, we again have individual locations or individual groupings based on a series or a mapping between the variables that we have. We create a centroid, which would be the center, and this is a statistical device. We want to maximize the effectiveness or the fit. So the centroid is calculated statistically, and then we look at the difference between the 2 different centroids groupings, and that will help us determine where, and how these 2 groups differentiate on each other. If we continue to look at our data, we can, let's do that one more page. Sorry, there's that. This is again an extension of what we saw earlier. We could look at those 2 distributions. We also look at this Z, which again is the function. That's the functional new data score that's created. And we'll see like along this line here, each observation will have a score. So we're going to have a whole bunch of observations that are here, and then we'll have a whole bunch of observations that are here. And if we created our distributions, we'd have a distribution for the orange group, and then a distribution for the red group, and they would be distinct. And so that's sort of how that'll work. So this line, this z here, is actually the linear discriminant function, and it's positioned again to maximize the difference between the groups as a function of the centroid that is ultimately created there. All right, so some other features or some other aspects here, outcomes and objectives then, generally speaking, of the discriminant analysis that we're running here. We want to be able to determine if statistically significant differences exist between two or more groups. And now these groups, very, very importantly, need to be defined in advance. So again, the dependent variable has to have levels associated with it that we know exist or that we think exist, and we need to be able to define them. So that's what we want to be able to do, and we want to identify, again, these independent variables or these dimensions, these IVs, that cause us to be able to identify the distinction that we think these groups have. We want to be able to identify the relative importance then of these independent variables as they predict group membership. So if we have a series of independent variables, some of those will be stronger than others in predicting group membership, and we want to know which ones those are. It may be we start with like 8 or 9 independent variables, and it might be we find only 3 or 4 of them are really significant in helping us determine which members are closest to which centroids and help us determine what the centroids would be. It's kind of like in regression where we may have independent variables that are not significant, their betas may not be significant. This would be the same case here where their weights might not be significant or particularly helpful in identifying groups, and some may be more helpful, and so that's what we want to be able to better understand. We also want to establish the number and the composition of dimensions of the discrimination between groups formed as we set up these individual as we input the individual variables. So again, what we're having here are different functions which are created. So okay, we have 3 levels maybe in our dependent variable, which means we have 2 functions that are formulas that will help create the groupings, and there'll be a centroid for each function, essentially, or the functions will help us identify the centroids. But these functions are also interpreted somewhat like a factor in factor analysis. So they may be interpreted, again, they may actually be named and identified as like we would in factor analysis, a grouping of variables that share similarities to each other. So a grouping of independent variables that share similarity to each other, and that can that can ultimately be used down the road, I guess, as a grouping mechanism type of a thing. Okay, so the functions that we see may be interpreted as well. The functional formulas based on the independent variables may also be used to be interpreted just like the groupings are. And finally, number 4 here, we want to be able to develop a procedure for classifying objects into their groups for a predictive measure down the road. So like we have the data, and this is data that exists presumably, and we know based on this data that certain individuals fall into certain groups based on their z-scores. Moving forward, we want to predict what objects in the future will be in what groups, without knowing what their actual behavior or actual group designation is in advance. So in other words, this is a forecasting method. So once we establish the function, the determinant functions, then we can apply those to future cases and be able to maybe predict, or definitely predict, group membership. Okay, so this is absolutely a prediction type of a thing that we want to be able to use moving forward. Some other aspects of dimensional or discriminant analysis that we need to remember. There are certain elements here, like assumptions, that we want to think about. So first and foremost, when we look at the dependent variable, the groups that we determine in advance. So this is something that we need to know in advance. And the objects that are making up the groups, our lines of data, have to be able to fall into each level, or one level, kind of exclusively, and those levels need to be exhaustive. So in other words, if I have 100 respondents and I have 3 levels, then all 100 respondents have to be in one of the 3 levels, and all 3 levels have to represent all the data. Okay, so the DVs, the levels need to be exclusive and exhaustive. We know that the dependent variable needs to be metric. If it is not metric, if it is continuous, then we need to be able to break up that metric data into non-metric data. Okay, so there are a couple different methods that can be used for that. There's the polar extreme method, and there are other methods too, but basically if I have a continuous dependent variable, one thing I may do is I may order my respondents from highest to lowest, and I might split the group up. I might split the respondents into maybe quartiles or something like that, and then I might take the bottom quartile and the top quartile, and I might recode them as high and low, and that would form 2 groups. So in other words, if I have continuous data that I want to use as a dependent variable, I have to convert it into a non-metric level data, something like that. Finally, when we talk about variables in and of themselves, they need to be what we call relevant, or they need to make sense. So the independent variables, then theoretically we would like them to have some rationale in terms of, kind of why we think they would exist. Okay, one other note then on converting metric to non-metric data. The most common approach then is to, again, take the data and just recategorize it. Again, we could break this up into thirds or quarters, or even take a mean split or something like that, and take the high group and the low group. It's certainly something we could do. I've also mentioned this idea, though, of polar extremes. Okay, where we have maybe 3 or 4 or 5 groups. We take the top group and the bottom group, and we compare those two. Now, clearly, we need to make sure that our sample size is large enough. If we're not using the middle group for analysis, we need to make sure the sample size is large enough to do that. And we need to make sure that there's no significant differences in other variables to indicate that these individuals behave differently, or they're from different populations. All right, so other things to consider as we move forward. Sample size is very similar to other multivariate analyses. We need to have at least 5 responses for every independent variable. This is a minimal expectation. data suggests or data prior research suggests that up to 20 observations per independent variable would be good as well. Also, in addition to that, remember we're grouping observations. So we have like multiple groups that are under analysis. We need to have at least 20 observations that are in each group. That would be the ideal number. So if we have three independent or three leveled groups, we need to have at least 60 observations, at least 20 observations in each group. We need to have at least the number of more than the number of observations per independent variable. So if I have 10 independent variables, I need to have at least 10 responses per level. But of course, that would be met anyways, so that's not that big a deal. Group sizes ideally should be close to equal. However, they don't have to be exactly equal, but in other words, if I have 3 groups, I should have roughly the same number of respondents in each group, so maybe 50 in each group or 20 in each group or something like that, 30 in each group. There will be a disproportionality problem if one of the groups is substantially larger than others. However, there are some statistical methods we deal with unequal groups a little bit, but ideally you want the groups to be fairly equal, approximately equal if they can be. All right, so some other than final assumptions, which would be, I think, probably pretty much expected with multivariate analysis. Typically, our IVs should be normally distributed, so we should double check for that. Heteroscedasticity would be an issue when we start thinking about equal variance across the independent variables. So we may check for the equal variance issues when we look at again heteros and homoscedasticity, multicollinearity. So that's something that we talk about fairly often, and data being linear, as well as outliers that may exist, and you may also throw in there missing data if it's a problem too. Linearity and non-normality. You may consider some transformations. One thing to remember here real quickly and importantly, discriminant analysis will standardize the data for you during the process of doing the analysis. So you don't need to be concerned about standardizing data in advance. So if you have data that has very different scales and things like that, the standardization of the data will happen as the process unfolds. Okay, so thanks for listening. Please feel free to touch base with me. Let me know if you have any questions. And this has just been a brief introduction to the reason, purpose, the objectives, and the general kind of concept behind discriminant analysis.